Okay. Hi everybody. So welcome back. Today, our plan is a little bit different for some reasons that I will mention. So there is no slides today. I would like to us to do some step back to see where we are and write some programs together, some assembly programs to understand, first of all, somehow more about computer architecture as always, but more specifically about MIPS, MIPS assembly programming and how we need to approach it. So far, you know that we have had several lectures discussing, talking about some instructions and the syntax of each instructions, also semantic of each instruction, which basically you may not be able to connect that much at this point, but hopefully after writing some assembly programs, you would be able to understand them better. And also you would be able, with the help of understanding and interpreting semantics of each instructions and the overall microarchitecture, you will be able to write more efficient programs and systems after all. So may I ask you to turn on your camera, as many as possible? More, please. So hopefully you also help all of us and interact throughout this session more to understand the stuff better. So hopefully this will help all of us to make a sense out of the course. Okay, do you have any question before we start? All good? Okay, so before we start writing some program, let's see what was the workflow so far, and basically why, first of all, we want to write some programs. Stepping back a little bit, we already discussed this, but I would like to put things into the context before jumping into writing some programs. Specifically, let's see why we want to write some program, and we have discussed this. So typically we have some problem, right? So we have a problem to solve. For this problem, we have a specification. For each problem, we have a specification about what is what we want to do. Like, for example, like simplest possible problem. Hello world, right? Hello world is a problem, right? What is the specification for hello world? Typically, you have a string, okay, and you want to print it out into the console, okay? So this is like a problem, and you have a specification for that. Another simple problem is, like, for example, adding two numbers, right? And the specification is like very simple, as we discussed. Like we have two numbers, two integer numbers, and we want to add them together and print the result, right? So problem is basically, for each problem you have a specification, and then like you need a machine in order to execute your program, right? So you have a machine which um, you want to instruct, and you want the machine to carry out the instruction in order to solve this problem, right? So essentially, so for each problem, you have a specification, okay? And in order to approach it, you need to, before even writing some program in a specific language, you want to be like a little bit more generic, and you want to write some algorithm for it, right? Without being constrained to syntax of a particular programming language, right? So you want to write some algorithm in order to essentially, without being again constrained to the syntax of a particular programming language, in order to have a very simple workflow to solve this problem, and understand like the steps that you need to carry out in order to solve this problem. For like hello world kind of problem, I mean, it's so simple, you probably don't need an algorithm for that, right? But for a complex problem, as you already know, writing an algorithm, writing the steps in order to solve the problem is going to be useful before even jumping into writing the code, okay? So once you have an algorithm, right? So you want to write this algorithm into a specific programming language, right? For that, so you need a language, right? And you write your program with a specific language, right? So for example, here, you may want to use C, C++, Java. I don't like Java, like, or whatever. You want to use in order to implement your algorithm, right? So you're going, as you see, we are going a step like one at a time, lower level, to getting close to the machine itself, right? So we need a particular programming language in order to write your program, okay? And then now, once you have your program, you want to obviously run your program on the machine, right? And you have a piece of hardware. You want to find a way in order to execute your code on top of this, or inside the machine, right? So here or maybe let's also build from the machine perspective. So far, like this perspective was from human perspective, but let's go on the other way around, right? So at the lowest possible level, you have some, like we discussed about this before, you have some electrons based on which basically you basically build the hardware designers, the manufacturers, material scientists, basically build transistors, for example, right? Build circuits where these circuits are digital, and basically you are able to wire them. You are able to make some um, logic gates, right? Um, and you're able to like like because this circuit, they you can, I mean, you can talk with them in terms of voltage, right? The voltage is either low or high, right? um, and in previous course, in logic design course, digital logic design course, you already know how to get from these low-level devices, transistors, to build some logic gates that they can do some more interesting logic. They can do like AND or XOR and so on, right? And then we have a gap here, right? So the machine are built from these circuits, right? That's a machine, right? But then, like, how these two pieces, how to these program and circuits, they talk with each other. So we need to fill this gap. Okay, and basically, and there are some characteristics that you want to have in order to fill this gap. For example, you could say, hey, I could find a way to translate for this particular machine X that I have, the program, my program, into this particular logic gates, do some hacking, and run my program there, right? Yeah, obviously you can do that. You can spend a lot of time like translate your fancy program into a set of logical instructions, and then find a way to carry out, to execute this particular program, and we are not talking about like the model of execution, one Neumann model yet, right? So imagine that we are before one Neumann model. Yeah, and then you could do that for this particular program that you already wrote, and then go and connect these circuits in a way in order to carry out your program, right? and get the result. What's the problem? The problem is that once you want to solve another problem, you need to do this translation like from scratch, and you need to spend a lot of time like doing all of this again and again for each single changes, or for different problems again and again. And this is very much cumbersome, right? And even if like you find another piece of hardware stuff, then you need to learn again how to do this translation, right? So it's two-way. And then over time, there has been so much progress so far. And one of the fundamental case, first of all, we discussed about this von Neumann model, which is a very simple fundamental idea in computing, which enabled us in order to have general purpose machine, meaning that we don't need to build machine for particular task, but the machine could be general purpose for any sort of task, and execute any sort of programs with this model, right? So with this von Neumann model, and then for that, obviously, people have started to think about some abstraction between program and these circuits in order to make these two different worlds as independent as possible, in a way that every time that there is a change in the way how you define your program and problems, and the way how you implement your hardware, you should not spend like a lot of time for basically stitching these two together. So, and the way that succeeded is through abstraction, through defining some contract. Okay, and this contract, and that was the topic of the whole topic that we basically discussed so far throughout this course, is instruction set architecture, right? The ISA, instruction set architecture, and this is a contract, you could say. And to clarify, contract meaning that, for example, the instruction that you have, right? The instruction themselves was part of the ISA, right? For example, we have discussed for LC3 and MIPS, specifically for MIPS, like several instructions, right? And these instructions, they are contract, meaning that nobody can change them, right? So when we say that we have a contract, nobody can change this contract. So this would stay the same forever, right? And if like, you could obviously have different ISA. You could like define like X86, for example, is a totally different ISA than these two ISA, right? But X86 ISA should stay the same forever, right? You might have different variations of this, like you might have a family of ISAs, but this contract would stay the same. And basically, key idea is to make basically to have a stable contract in order to make this translation happen and become as less painful as much as possible, right? And like in order to make this happen, in order to connect these two worlds together, we need another piece which we will talk in the second half of this course, is about the microarchitecture. Okay, and the microarchitecture is basically the way how you implement the ISA, the way how you implement this contract. Okay, and for one ISA, like for MIPS, you could have so many different microarchitectures, right? You could have thousands different microarchitectures for even MIPS. For x86, you could have like enormous number of microarchitecture, right? What is the difference between them? Maybe you could say like performance. Yeah, one say, okay, I was able to come up with this idea and like implement this contract and get like 10x performance comparing with the other like the state-of-the-art microarchitecture, right? Performance is one thing, cost is one other thing. Like I was able to come up with this new idea that could cut the cost of implementing this contract to half. Okay, that's fine. You could have different ideas. You could have different way of implementing this contract, and that's fine. As long as you basically your microarchitecture can implement the ISA fully and be consistent, right? Because we do not want to violate whatever it is written in ISA. But as long as you you implement correctly with the correct semantic, everything basically works. You it doesn't really matter. Okay, and you are able to without changing your program to port your program and execute it in another machine, right? That's why we have these like these two important layers to make this portability happen, to get different performance, to get different cost, and be able to run programs more efficiently and so on. And again, to repeat that, throughout this course, we want to understand these two layers, two important layers, more deeply. Okay, and basically be able to also write some programs for particular ISA MIPS specifically. The type of program that we write in this course is MIPS assembly that we will start from today in order to because that's writing assembly program is one of the very important part of understanding computer architecture. But again, to already you might have several questions, right, in your head. I mean, I expected you to ask, but I can ask instead of you, right? You could say like, who cares about like MIPS, or who cares about LC3, right? And by the way, like I mentioned that, I mean, LC3 probably no one cares, right? Because it's a ISA is only for teaching, but MIPS, there are so many CPUs, MIPS CPU out there, like billions of devices are powered by MIPS CPU. So it's everywhere, like it's similarly to x86 type of CPU, Intel CPU that you have it at home, it's everywhere, or ARM CPUs, where we all have it in our mobile devices. MIPS has been popular, still is popular. MIPS CPU is, you can find them on like small devices and so on. But there are like at the scale of billions is out there. But again, like you might say, okay, like, yeah, sure. But like, again, like why it is important, this particular type of ISA, this particular type of assembly, you know, the answer is also simple. Here we want to understand the fundamentals. And that's why I mentioned you don't need to memorize the syntax of this. You will have in your exam and everything, like for solving homework, project, etc. You have a list of instruction, and you can look at it, and like you can use the right instruction at a particular place, right? But understanding the fundamental of writing assembly program and making sense, also later part of the course, understanding the fundamentals of building a microarchitecture of implementing the ISA is also very important. So again, more specifically, in order to understand ISA or talk in the language of ISA, is to write assembly program. Okay, so it is this. And you can like already here see that, like you could even like this layer, this program layer, you could like split it in at a lower level. You can say assembly. This is the language which is bound to your particular ISA, right? Like X assembly. Right? X could be MIPS assembly, could be ARM assembly, could be like x86 assembly, right? But you typically write your program with a general purpose language like C, right? So you could consider this layer of program like lower level, which is binded to the ISA, the assembly, which you in which you use the instructions in your ISA, which is binded to your particular ISA, and that's what we are going to do. Any question so far? Okay, that's very good. I have a question, like how we are going to get from a general purpose language like C to assembly. Do you have any idea? Yes, go ahead, Ralph.
Well, I know with like if you were using like GDB, like you could use GDB to get down to x86 if you were coding in C, which is like I was just trying to do that and I failed, but I know that's the way you can do it if you know how to use GDB.
Right, and yes, that's right. And typically, this is how it happens, right? I mean, again, at the end of the day, I'm talking about this because it's very important to understand the importance of all of this, right? Because again, you might say, okay, maybe I never ever needed to write any sort of assembly programs, and that might be right. I mean, there are some like very special cases. You may want to, and you should write probably in assembly, because there's no way, for example, you could you could, for example, the cases where like you want to improve performance by like a fraction of time, or you have like very limited resources on a device, and you cannot load large program. The only thing that you can execute is just some assembly code. There are special cases like you really need to, like, that's the only thing that you can do. But in like almost all scenarios, again, like you write your program in high level language, and even like considering also, maybe let's also consider like this layer, right? Because assembly is also something we understand. Like machine do not understand assemblies. At the end of the day, is a language. Machine understand machine code, these 0 1s, right? So basically, this is the machine code that that you need and sit in the memory, as we discussed, the memory of your machine, and get executed one by one, with this notion of or model of von Neumann. And that's why, like, and there are some reasons, we will go through it, the cases where, I mean, there are several reasons that assembly comparing with the machine code is useful, right? First of all, it's very difficult to like understand these zero ones, even if you memorize the specific pattern of zero ones, that this means, like, for example, this means like doing this, okay? This pattern mean doing Y, okay? But still, for us human, it's really difficult to do a very complicated thing or task with zero ones, because these are like very difficult. I mean, some people, they are able to do it, but like for normal people, not really. So, and there are also other reasons. We can talk in more detail once you see some example of assembly. For example, when you write a code, like with zero ones, whenever you want to change, like remove a line of code, basically this means that, for example, you remove one line from the memory. This means that the memory addresses of like the other location that you used in your program might change, right? And then you need to like change several other instruction as a result, because of this movement of like instruction in the memory. And this becomes a mess if you have a large program, and that's becoming intractable for us to adjust. So any sort of changes even in the program become somehow impossible. But with assembly program, like these are encoded as like some sort of a label, as you will see soon. Like you don't need to be worried about like later on. Um, so this is the workflow typically. So you have your program in like C, for example, and then your compiler compile it to assembly, right? This is like assembly code, right? But there are some more detail that either you will learn throughout this course or some other courses like compiler, operating system, and so on. So there are some bits and pieces, details that like throughout your studies, at some point you will figure out the whole thing and like be able to see the whole thing together. And here you have machine code, right? So this is the task of assembler, to translate assembly code into machine code, right? This is what assembler does. Okay. Any question about this so far? But again, like there are some detail I don't want to go through it and confuse you. For example, like where are the other libraries that I used in my program where they are going to be linked and so on. You will learn in other courses like compiler, right, linkers, stuff that these things will be automatically will taken, and as a result, all of this will be will become an object code where you can run in the machine. Okay, that was very good. Let me see. Before we go into more detail, do you have any question about what we have discussed? I want you to be really clear about everything. That's the only way you can learn about computer architecture. So if you have any question about these is stuff that we discussed so far, let me know. And I'm happy to clarify all of this for you. Let's see whether so basically, yeah, you have, and now what I'm going to do is to also show you the workflow that you need to carry out. I will put this instruction in detail in the course website, obviously. Because you need these in order to write programs and do stuff and do your homework and project and so on. So you need these details, but I'm going to walk you through these today, so you'll be able to start writing assembly programs as soon as possible. Yes, and here, like, then this will be translated to right after you link everything together. You have your executable thing, but then after you have your executable, you need to also load it into your memory, right? because this is where actually the instruction sits, right, inside the memory, at least with the one Newman model, right? So you need to, and this task will be done by loader, right? But you will learn about all of these in some other courses. So you have basically from this high-level code in like C, there are some steps that you need to go through, or your program will go through, and these are like, if you could think about it, these are some sort of like typically transformations. All of this, like what compiler does, it does some sort of transformation. I mean, you could call it optimization, but at the end of the day, all of these are some sort of transformations that happen in order to translate your high-level code into some instruction that or machine code that sits inside the memory. Okay. Let's see. Okay, there is question. When we start doing assembly, what program will we use for it? Yeah, I'm going to talk about it now. That's a good question. Okay. Let me share the screen. Do you see my screen? Okay. Sounds good. Okay, so here we have few things to discuss, specifically about this workflow that you need to do, like about assembly programming and stuff, right? So again, first of all, for writing assembly is like a normal code, like a C, you need an editor, okay? So you need an editor, and you can use different editor for writing assembly. You can use, for example, here I have Sublime text in the middle, right? You can write your assembly in Sublime for like almost all editor that you want to use. There are some syntax highlighter that you can use in order to make your coding more efficient. As you know, I mean, I typically write either in Sublime or here I have also Visual Studio code that I use. You can also use Vim if you want. There are syntax highlighter for that. For example, for Visual Studio, see here, you can find it very easily. You can install extension, right, and then go and find MIPS. Like yes, here there are multiple different options. For example, here I use this one, right? MIPS support. You install it. And when you write code, it recognizes MIPS instruction, and like it, you enjoy it better, right? Also the same for Sublime Text. Here you can install package, and then you can write MIPS and find it already. Since I install it, you don't see it here in the list, but basically, if you try to install MIPS package, you can install it, and here down there, like also, by the way, you can also use Atom if you want. There are also extension for that in order to help you. Here, for example, I can change syntax highlighter. Here you see MIPS. Currently it's plain text. You can change it to MIPS, and then like see it has auto compilation. Like for LI, it helps you to write your assembly code a lot more efficiently. Right, and so on. The same way for and also for, I will put some instruction for all of this, how to do it exactly, but I'm sure you can do it yourself. Here, let's see. Let's say we want to write hello world, right? You can use the extension ASM or S, right, for assembly, and you can write your assembly code here, right? Like for example, here the same, like it has some auto completion feature, which is helpful. One interesting feature of Visual Studio might be the case that like it automatically write the comments in assembly. You can write comments similarly to high-level language like C, and it's I strongly suggest recommend it because it makes your code a lot more readable, and you can understand it. I can understand what you wrote and so on. So like when you write your code for the project and for your homework and stuff, make sure that you write comments for your code, and it's a good practice anyway, right? See, for example, if I this is load immediate, right? You hopefully remember that. So when I like see how automatically it writes the comments, right? So load immediate, if you remember, you have one register and you have one immediate value, which assign it to this particular register here. Like I used like T1. T1 was like one of those register in MIPS, right? Or T0. See, it automatically changes the comments for you. Where like here in Sublime, it doesn't. So you need to write the comment yourself. Say I change it to hello the world, and I need to change this. It like by default, I don't know why it uses R, but anyway. So see, it also have some interesting stuff when it does auto completion. You see, it also provides some sort of hints about the semantic of each instruction as well. But for example, here, like, let's imagine you want to do T1 and see, like, it highlighted, it recognizes this particular MIPS register, right? If you remember, T1 was one of those registers, and we had how many register? 32, right? And here it puts immediate, so you can put the immediate here, like 3, and then you need to write comments, right? You can write comments like you need to write your comment here, for example, yourself, if you want, and again, there are some restrictions, or there are some, like for example, in assembly, you cannot have multiple instructions into one line, right? So each line, one instruction, okay? But you could have comments similarly, right in front of it or on top of it, however you would like, and so on. So here is like the first step. You need a text editor in order to write your program, assembly program. What else? You have again several options. You have like Emacs, Vim, if you want to use Sublime, Visual Studio, VS, or Atom. These are pretty much it. You may find some other alternatives as well. Is there any question here? Yeah, it is Visual Studio Code. That's right. .s is basically like when you write assembly, like similarly to C, like you use .c to show that this is a C code, right? .s for assembly or .asm. Okay. Now, another thing that you need as a part of your workflow is how you want to execute your assembly, okay? Because you might say, hey, I don't have any MIPS CPU. How can I make sure that the program that I wrote ever gonna get executed, and whether there is a bug or how I'm going to get any feedback, or if I want to measure something, and if I want to trace my program, whatever the way as you do with high-level programming language, what's the process for that? Since we don't have MIPS CPU. Yeah, that's obviously one way. If you have a MIPS CPU, you can go write your program assembly, execute it in the CPU, in MIPS CPU, and get your results. But here, on all of us, we have some general purpose laptop, computer, whatever, right? Typically runs with Intel CPUs, and the alternative solution is to use some simulator. So there are several different simulator for MIPS, and in this course we are going to use a particular simulator. It's called SPIM. It's called SPIM, and you can find it here. Yeah, in this address. I will again send you all of this. And there are it supports multiple different platforms that you can use. You can download it, the executable from this link, and you can also download the source code and build the code for your machine if you want. But there are already executable here where you can just simply install it. And in particular, for a SPIM, you can use here Qt SPIM. SPIM has three variations that you can use. I mean, you can use two of them on your computer. It has basically a graphical interface where you see here. It also have
so everything you do is brought down to this
hello,
it's converted into this. Oh.
Yeah, if there is a question, let me know. So basically, this is the GUI for, again, this is, to clarify, this is simulator or emulator of MIPS, okay? What it means, this is important to understand. It means that this simulator, obviously, it is running in my machine, which is Intel CPU, as an Intel CPU. So basically, in a way, it emulates in a way that it emulates MIPS. So So you can basically run your assembly code with this emulator, and your code thinks that it is running on a real MIPS machine when you load it and when you run your code here inside the emulator, right? So this is, think about it as a virtual machine simulator, however you want to call it. So you can run your MIPS assembly code with a spin. And again, the GUI version is called Qt Spin. Here, I will talk about like what are these shortly, but typically like you can, for example, let's say you can load your program, like for example here, the program that you wrote here by as simple as this. And in the text, here you see some instructions. Some of these might be familiar to you, like the first one is load word, and several others. These are the default instructions for the Spin itself. So when you load your code, it will be located down here. You will see the update. You have some registers here. You see the list of all of the registers for MIPS. Like you have 32 in total, right? Here are the 32 registers that you have in MIPS, okay? You have some special purpose registers as well. You remember one of them, at least PC. PC was one of those special purpose MIPS. And in general, in all of von Neumann type of model PCs, you need PC program counter pointing to the current instruction that the CPU needs to execute, and some other like a special purpose that like we'll talk about them later on, but we have not yet about these special purpose like a status, you know. EPC cause, like for example, EPCs, a special purpose register when like if exception happen, basically it saves the location and also in the cause of the exception. It is used, these two specifically, it is used for debugging. And you see some other like high-low stuff. We'll talk about them later on. But essentially you see some sort of registers here. These are floating point registers. Mainly we'll use this integer registers. And here you see in the data tab, you see what basically the memory, what is inside the memory in terms of here are the addresses of the memory, right? Again, each memory you see here and these are like the addresses are in terms of hex again, the encoding and so on, and also the content of this particular memory, right? What is in there and so on. Okay. So things become more clear, and also you can use command line for Spin. I think I have command line for assume, yes. So we can also use a command line and get the same functionality from command line. Like for example, sometimes like depending on how comfortable you are, whether you would like to work with command line, with Spim command line is interactive. Like for example, I can load particular like program from command line, right? What I had here, like let's say I want to load hello world.s, right? Right. So it loads the program, and then you can run your code by this interaction. So now I ran the code and it says that instruction undefined, like because the code is not valid anyway. This is one line of code that we wrote without like obeying to the syntax of assembly, at least the MIPS assembly language. So you need to go and change a well-defined code in order to run. So you can basically run your code, and there are some, for example, there are some other functionality for debugging and so on. Like for example, print. This command will print all of the registers and the content of register, right? You can also print particular register, right? As far as I know. Yeah. So here, for example, you need to, you remember $0, that is always 0, right? So it shows you the content of this, any register that you want. So like it helps you to debug your code interactively and run it and so on. Any questions so far? Is there any question? For example, you can also step inside your code, right? So for example, you can step like one saying that like execute one line of code and so on. So it gives you essentially some interface that you can pretty much like these two version of Spim are the same. Like it gives you all the functionality that you need to run, debug your code, like one in visual way with GUI, one with command line interface. There is a question, can you do it in one line or do you need to enter the Spim environment? You can do it either way. You can, I mean, if you want to run, you can just see exit, like Okay. Like here, for example, I want to say I can run it this way, get the result. It says that it's undefined, right? One of the thing, at least the assembly code that you need to write for running with this emulator, you need to define main label, which we'll talk shortly. I mean, we don't have much time, but and that's why it is complaining. So that's why. But let's maybe at least try to, if you bear with me, try to write a very simple program, the uh, the hello world, correct hello world. So we see some results and do this debugging, but we need to go over time if you don't mind. So I give you like maybe let's have 2 minutes break, and then we spend some time to write a very simple program together and like run it and see the result. So like 2 minutes. Okay. Can you please turn on your camera so I can see you? Awesome. Okay, let's write some code together. Let me close this. Maybe let's start. So we again start from the top to go through the workflow quickly. We want to write hello world, right? So let's be clear. Maybe to do the full. Let's first like write a specification, right? Like for hello world, the specification is very simple, right? Right. Okay. Very simple a specification. So you know what is a specification. A specification for a program could be written in like natural language like English. You could have some domain-specific language for writing a specification of your program. Sometimes you may want to have some examples as a part of your specification, meaning like input output example of your program. For example, when you write when you want to write a specification for like adding two number, maybe you could write also one example, 2 plus 2 equal to 4, right? Pre-post condition and stuff. But that's not what we want, but somehow wanted to like start from the top. And then next, based on this specification, we want to write some code in high-level language like C, like in C, we want to write some code in order to implement like our idea, right? We want to write a very simple code. We want to basically we want to print print this sentence, right? That we wrote in the specification. We need to declare we need the studio IO, right? In order to do this, right? We can use printf, right? And then here we can maybe go to a specification. And use it here. Okay. This could be could be our C code doing doing our stuff, right? So here we could so here we see the hello world C, right? We could use GCC in order to compile it, right? Mm-hmm. There's no.
Professor?
Yeah.
I think it's because you named it Hello World with a W after hello.
Oh, haha, good catch. Right, let's call it HW. And now we have the executable, right? Done, right? So at least we got it in C. Okay. And like one way to get some assembly code, you know, that the compiler also does that. Now we don't want to do it now, like with GCC. You'll be able to get your assembly. I mean, in GCC, for example, in Mac, I'm running it in Mac. I won't be able to generate like MIPS assembly, but I'll be able to generate like x86 assembly for and some other type of architectures from this family. So here, like, for example, with this S, it only run pre-process and compilation step, where basically it gives you assembly code as a result. So it doesn't do all the way down to executable. So it only does the compilation, which if you remember, compilation only gives you the assembly code, right? Maybe we could try that. Did they spit out the assembly code? We have so many stuff here. Yeah. See, this is the assembly code that GCC produced, right? here is with the syntax highlighting, right? And you see that it is not that much familiar with you. At least you don't see like any instruction that you can recognize from what we have discussed so far. Because why? It is not MIPS assembly, like it's x86 assembly, right? What do you see that this line that we use in printf? So this is like corresponding the assembly code for x86 machine that we get from GCC. You can get the same through Clang as well, right? With Clang, you could also use same stuff to get the assembly code, and also you can specify particular architecture. Like here with the target, you can specify a particular architecture in order to generate for different type of architectures, right? Different type of ISA, and you will see as a result maybe a slightly different instructions, but like more or less same sort of stuff will be generated. Okay, so now obviously we don't have a MIPS assembly yet, but let's do it. Again, I wanted to show you that you'll be able to generate some assembly code with GCC and other compiler that you have. But again, for this course, we want to learn how to write assembly code ourselves, right? Basically, the translator is us. We need to like do this translation from like C code to assembly code ourselves. So we are the compiler that does the job. And like in your homework and exams and so on, you will see these like questions that we give you a like code in C, and we ask you to translate it into assembly. Or like instead of C could be like English in sort of a specification, you could say, but like a specification through C code might be more precise in order to do this translation. Okay. Now let's write. Okay. Let's do it. It's very simple. In order to do that, there are some basically syntax that you need to obey in, like, for example, any assembly programs, right? There are some convention, like there are some sections where I mean, like we discussed like about comments, we discussed about this, like no 2 lines of code, 2 instruction in 1 line of code and stuff. But there are some, one other very useful thing in MIPS and other assembly, you can use these labels. Labels is like the essential thing. It's very important to use. And essentially is labels are like very simple. Like, for example, here I define a label. Like here I define a label. Okay. Basically, it's you use word and then you appended it with comma color, right? And then you have some directives that help you to define some sections, right? For example, you can define a directive for data, right? Where you can define like the data that you need to have. For example, when you have a string of character, you want to, for example, when you have a constant, you want to define it there. Okay. Any questions so far? Let me see whether there is something else. Yeah, these are like, and obviously like you need to like know at least like instructions, but instruction, again, like we give you, like even for your exam, you can use list of instruction and so on. So you don't need to memorize it or anything. So that would be easy. So let's go ahead and implement this simple program, right? So what we need is to have we need to define this constant that we have, right? And this constant, like let's say, we can define it in the data section, right? Like, for example, we define it in terms of like message, like we use it, say, how can I, for each message, like for each label, like data, for example, you need to define its type, right? And like similar to like could be integer, could be string, so on. Like here, for example, I want to use some ASCII code to specify this message that I had in the specification, right? So I had this in my specification, so I copy that. And like in MIPS assembly, this is what you can use for defining ASCII code, and then see, it recognizes, for example, this and highlighted it for you, so it's the legit type that I use here. So I said that I need to define this label message that I'm going to use it in my program here in the main. Okay. And again, we need for any assembly program in MIPS, you need to have this main where you define, like, this is similarly as the main in C, C code here we have, right? And like you can also define like your code right away here, but maybe you want to like indent it so it becomes more readable in order to make your code basically a lot more readable, right? So again, if you remember this data, I want to correspond it with what you have learned so far. This data is sitting where? Is sitting inside your memory. If you remember the lecture, and we need to, when we want to run or use it in the program, we need to put it somewhere in one of those registers in order to use it. Okay, so we need to basically we need to load it into a register, this content of the memory. So if you remember, for example, one of the instruction that we had was basically LA load address, where you specify an address of a memory. In this case, like this address, like was a particular number, but here, like we have the benefit of using label for referring to this address. Right here, we use variable like message. Okay, and then we could use like T1 here, right? Or we could use like anything really. But one other thing that you need to know here, like I'm thinking out loud in order to help you to how you need to figure out how to write program. But you already have experienced that in some other languages, right? But in assembly, in order now, we need to call, we need to get some help from operating system in order to print out the content of a message into the console, right? So there are some particular function that basically you can call from your assembly in order to do the job. And this function, we can think about it as a utility function of your operating system that does this for you. So you don't need to implement printf in this case, right? So this is the task of operating system that help you to do that. But one convention that you need to know is when you want to call a function, you need to introduce its argument, right? You need to give it some input. In this case, the input is like the content of this message, right? That we have it here. And in MIPS, there are some particular arguments that register that you can use to pass the argument to a function. And these are A0, A1, and A2. We'll talk about it, like what would happen if we have more than 3 arguments in a function. But that's not a problem here. We have only like one thing to pass, and we basically we pass it to A0, the first register that are supposed to do. But remember, like, you have A0, A1, and A2. Only this register in order to do this. So now you have the address of this message in the memory. Okay. Now you need to basically, there is one specific command instruction in MIPS, which is called syscall, that you can use in order to do this task. But syscall is like generic. Syscall, when you when your machine call this, it basically call your ask your operating system, what should I do? So you need to tell your operating system what a specific command I want to use. And in this case, a specific command is printf. The way how you can tell your operating system, because it has several different system command that you can call, which one to call, you need to tell it through a specific register. You need to use a specific code in very specific register, and in this case is basically what you need to do is to tell, for example, through V0 that I want to use printf, right? And printf turns out to be number 4. Okay, so this turns out to be number 4. So when you put 4 inside, and you remember li was what? Load immediate. So that was one of the instruction that you could use immediate here as a argument to load it into particular register here, is a one of those 32 general purpose registers in MIPS that you can use. But when you load this number before syscall, it tells your operating system that I want to use printf, please, and use the address of my message, and you can find the content of if inside memory, which was located in the address that you you specified in A0. Okay. Okay, so this is clear. What happened to 4? Any questions so far? So now basically what it does, it calls operating system where basically print a string for you, and once it does, it comes back again to the next line of code. Okay, and the next line of code here was return 0. Okay, and return 0, it's also again, if you remember, like here, we want to pass a particular number. Sorry, here we want to pass a particular number to the operating system. So we could use li the same way. Say, hey, I want to return 0, and then jump and register. And there is a particular register. It's called RA. You see it where it is. Here, there you go. The last bit register. You see it 0. It's initialized in 0, but here you say that I want to jump to register RA. This is basically once you're done in a method, right? So once you're done with your task in a particular method, you need to jump into basically to a particular point in order to carry on with the rest of the instruction that you had so far. So this is typically where you end when you end your code in assembly, and then we are done. So that was the I guess the only thing we needed to do. Then we can make it more readable. Okay. Hopefully this will run. So you clean your code. And then let's use the Spim to see whether we can run our code or not. What was the name of the code? Hello, old MIPS. There you go. Right? Easy, wasn't it? So you could also run it by doing this interactively. So you need to first load hello world. What's it mean? You need to first load it in the memory of your emulator. So it loads it to emulator, and then you can say run, and it runs. Or you can say that oh, see, I used the wrong name and it couldn't recognize it. So now it loads it, right? And then you can also like let's do some debugging here, right? So if you look at the program, here we use A0 in order to copy the address of the message, right? So see, the content of A0 is 0 now, right? Now let's maybe run until a certain point to see what is the content, whether the content of this this register would change or not. Okay, so you can step inside your code. So this is where this is not our code. Yes, this step is not our code. Step 6, right? How many? A Steam has like several lines of code that needs to get executed before like our code get executed, right? So yes, so here here you see that. Oh, this is one important thing. One important thing that I need to mention, and you better to know about it now. If you remember, in the code we use like load address in order to load the address of message into A1, but load address is not a real MIPS instruction. It's what it's called a pseudo instruction. Okay. So pseudo instruction are useful because these are the instructions that typically programmers use in their code, and it facilitates writing more efficient, or like facilitate the workflow of programmers, and that's why we have pseudo instruction in MIPS. And like here, you know, like this emulator would translate it to the actual MIPS instruction. Here you see that it's used LUI, load upper immediate, right, to load the upper immediate part of this into A1, and then basically do ORI in order to get the whole address, right? So if we do now, let's see. See here, so it uses a combination of LUI and ORI, or immediate. If you remember this combination, it basically loads 32-bit address into the register. You need to use both in combination in order to do that. But here we use one instruction in order to do the job. But this translation, like your assembler in this case, does this automatically. What else? Yeah. Let's print the content of A1. See, the content of A1 now has changed. So previously was this one. Now this is the content of A1, where basically the message sits. Okay. But maybe because like let me show you again. Or maybe let's try it with the GUI to also see the other aspect of it, right? So here. See, this is where our code is sitting, and here this is our message, right? And our message, if you remember, since it was too long, obviously didn't fit into like one word, and we needed to occupy multiple words in the memory. As you see, it is from this location, and this location. So you have obviously multiple words memory location in order to store the whole string, but it started at this particular point in the memory. So you only need this the beginning of the string, where the beginning is located. Okay, and once you have this, you can like run it. So this is what's going on here? I think there was an error somewhere. Let's maybe, one way of doing this also, you can like do some debugging. You can put some breakpoints here, and you can execute your code one line by line. So you can basically You can obviously execute one by line, but you can also set breakpoints. So in order to stop it there, it says that this is your breakpoint. Do you want to continue? You can either continue to execute it, or you can say single step, right? This is how you want to use, right? So you want to use single step to see what you're going to do. Right here at this stage, you see what is the content of R1, right? And then you again do single step, and then you have here change the A0. This is what you wanted to do in these two instructions. This is like here. And now we want to change V0, register number 2 here to 4, right? Which happened, right? And then do the system call. At this point, I expected to see the result of typically the console should appear. I'm not sure why it is not showing the console. Shows a very simple window showing you the message in this case. But anyway, now you see one execution path of this program. So you know how to work with both QTSPin, which is like the GUI version of your assembler, and here command line. Probably command line is easier. I don't know. Let me answer your questions. Oh, that's right. We need to enable it. Good point. Awesome. See, the message is already there. Yep. Very good point. So in your window, you need to, by default, enable it in order to show it for you. You can change like these also if you want. Like if you want to get rid of FP register, you can do that, or you can like change this. But essentially, you have, as I said, you have the same functionality with both. Okay. Yes, this will be recorded and is being recorded. You can, right, okay. Jacob, I'm not sure what is your question. but yeah, like we did the whole process again from scratch, from a specification to C, high-level language, and then assembly. All we did it ourselves, right? In order to show you like the whole process of doing this. For this course, obviously, your task is to write assembly. This is like, you are not going to ask you to write in C code, like, but you are given like C code, and we ask you to translate it into assembly, MIPS assembly. Okay. Good. Is there any other questions? If not, then let's call it. But I'm going to also walk you through some more complex programs beyond Hello World, so you see how to write a program where, like, you need to, for example, like calculate something, like say you want to add two numbers together, you want to maybe maybe like you have an array of numbers, you want to sort it, like do these normal problems that you typically encountered, and solve it in like C or other languages, but now we want to do it in assembly. And one thing that I can say, similarly to other types of programming, again, this become easier as you write more programs, and basically understand the features, different features of the language, different maybe best practices, different way of thinking about problem solving in assembly is slightly different level of abstraction than like a language, a high-level language like C. But anyway, I repeat that again and again, that you need to understand the fundamental. And one aspect of learning about computer architecture is like learning its language, right? Okay. Have a good evening. Bye.